Okay, we're back to chapter 18, part 2. So this chapter is about how to represent cellular networks using transfer functions. And in the last chapter, in the last part, I looked at the transfer functions for the state variables. So in this part two of the chapter, I want to look at how to represent transfer functions for the fluxes. Okay, so the flux is a steady state reaction rate through a pathway. Okay. So for a linear, just say you had a linear chain like this of 3 reactions, and I'm going to assume x0 is fixed and x1 is fixed. So v1, v2, v3. The flux at steady state, v1 equals v2 equals v3, and so the flux could be any one of the 3. And in general, we just refer to one flux J for all 3 because they're all the same. Okay, so how do we work out then Hj S? Well, the way we do that is by considering the output equation. The output equation formalism, which was yt equals c xt plus d, and then there was an input here, pt. Okay, and these are the two matrices C and D. Now we can do exactly the same thing as we did before. We need to have an equation that gives us the flux. So I'm going to call the flux J, and I know that the flux is some function of either v1, v2, or v3. So I'll just call it v. So it's some function of v, and I know x is a function of the state variables and any inputs that happen to be affecting v. So v here can be v1, v2, or v3. It doesn't matter. So when I linearize that, I will get, now we're not talking about a differential equation here, okay? This is just an algebraic equation. So I get delta J on that side, then I get dV by dx, delta x, plus dV by dP, delta P, okay? So what I want to do with that is, and we're already talking about steady state, what I want to do is take that into the Laplace domain, and I'll call, let's see, what should we call it? So I'll call it a plus of the left-hand side, h of j of s, okay, equals, let's see, let me get it right here. Yeah, so it's c times x of s plus d times p of s, right? So I've taken just the Laplace transform on both sides. The c is the dv by dx, and the d is the dv by dp, okay? Now, what was x? What is x? X of s? Well, x of s, I need to consider h of x here. So I know that x of s equals h of x s times whatever the input was. And I'm just going to indicate it with p of s. I'm not specifying what kind of input it is, just that there was an input p of s. So what I can do is I can insert this then into there, and then I end up with h of j s equals, and if I write it out fully, right, I'll write it out fully, the c becomes dj of x, the h of s becomes si minus, remember this is what we had before, dx to the minus 1, then we had another n, then dv by dp, and then finally this piece here plus dv by dp, okay? So that's the transfer function of a flux. All right. So with that, we can now. That's basically what we. Those are the two main equations we need: Hj of s and Hs of x. Note that at zero frequency. Okay, when we set h of x 0, we set s to 0, or hj of 0. These effectively equal the sensitivities, the unscaled sensitivities. So that's dx by dp, and this one is dj by dp. Okay, so those are these tell us how sensitive the state variable is to changes in p, and this tells us how the fluxes are how sensitive the fluxes are to changes in p. And of course, it's up to us what we want p to be. So let's do an example, shall we? So let's do an example of deriving this thing. Let's have a linear chain this time. Okay. We have x1. Both of these are fixed. Okay, fixed. And that's catalyzed by enzyme E1, catalyzed by enzyme E2, catalyzed by enzyme E3. These are the rates through each of the reactions V1, V2, and V3. Okay. All right. Now, as inputs, I'm going to assume three possible inputs, E1, E2, and E3. These are natural inputs to consider if you're designing drugs or you're doing metabolic engineering, because drugs basically bind to enzymes and proteins and change the phenotype. So we're going to consider all three here. As we did before, I need some of the numbers. I know that the number of state variables is 2, number of reactions is 3, number of inputs is 3, E1, E2, and E3. All right. I'll need the stoichiometry matrix N, and for this one, it's 1, -1, 0, 0, 1, -1. Okay. The dV by dx matrix, that'll be a 3 by 2. All right, it'll be a 3 by 2. We can just write some of the elements down here. So that's dv1 x1. The next one is dv2 dx2. Well, let's do them all, shall we? And for dx3. Sorry, that's wrong. That should be a 1. Sorry about that. And then dx1. And then we move on to dx2. So dv1 dx2, dv2 dx2, dv3 dx2, and that's the dv by dx matrix. Now, some of these values may be 0, some of them may not. It all depends on how we treat these rate laws, whether they're reversible or irreversible or whatever. Okay, what about the parameter one? Now we've got 3 parameters. This will be n times q, which is 3 by 3. So it has 3 by 3. It's a 3 by 3 matrix. Okay, whoops, 3 by 3 matrix. All right. The top one I know will definitely be dv1, de1. Now these ones, one here and here and here and here, all those are 0 because I'm going to assume. Let's look at all let's look at if we go down here, this one would be V2 E1. Now, I'm going to assume that the enzymes only affect their particular reaction. So there's no crosstalk between E1 and the second reaction, or crosstalk between E3 and the first reaction. They work independently. They only catalyze their specific reaction and none other. That means these terms, all the off-diagonal terms, have to be 0. Okay, so this one becomes 0, 0. That becomes 0. That becomes 0. And then in here, basically, it's the main diagonal gets entries. Okay, that's 0. That's 0. And then finally that one. All right, so it's only the main diagonal have entries. Okay, the off diagonals don't, because we're assuming all the enzymes only act on the respective reaction rates. Now I can put this together in this equation here. All right, I can put all that in, and if I do that, I get actually the characteristic equation is very similar to what I got before. It was x squared plus, what was it? dv2 dvx1 plus dv3 dx2 times s plus dv2 dx1 dv2. Oops, that should be a dv1. Sorry. Let's do that again. dv1 dx1, that's dv2 dx2. Okay, so that's what the characteristic equation looks like. Or they're all positive terms, so the system, the roots are all negative. The roots are negative. I know they're negative because all the terms are positive. This coefficient is positive. I know this is positive. I know this is positive. I know this is positive, and the whole thing is positive. right? I know this is positive and I know this is positive, so that's positive. So all the signs are the same, so the only roots are negative. So in other words, this system is stable as well, not surprisingly, of course. All right. I can work out the the HJSs in the same way as I did for the HXs, but it's just a little bit more tedious to do. It's the kind of thing that's done better with something like Mathematica or whatever. But it's possible to do it, and we'll see some examples in later chapters on this. Okay. What else? One other thing I want to mention are these things that we've talked about before, the canonical transfer functions. Now, these are a special case when all inputs are the enzymes, every enzyme, okay? So let's see if we write this, let's write the h of x down, for example, just to show you what I mean. So this is sin dv by dx to the minus 1 and dv by dp. Now, before I put the p down, let's say we're dealing with all the enzymes, so I could put, dv by de. The other thing, assuming all the enzymes only act in the respective reactions, I'll get a main diagonal and everything else is 0. Now for a matrix like A, let's say A0, 0B, the inverse of that is just 1 over A, 0, 0, 1 over B, okay? So I can compute the inverse of this, no problem. So if I post-multiply both sides of this equation by the inverse of this, I will get hx of s times dv by de inverse, I'm going to post multiply by the inverse, si plus n dv by dx inverse n. Note here, if I multiply by the inverse, this thing becomes the identity matrix, so I can ignore. So what I'm going to do, I'm going to define this thing then as a special, another kind of transfer function that has been sort of normalized by the input strength, and I'll call these canonical transfer functions. So they're also a function of s, of course, but they basically, for the x1, it's just si minus n dv dx to the minus 1 times n, and that's it. Then for the flux one, I'm not very good at doing those calligraphic C's. It's s, it's dv by dx. I won't bother putting the whole thing. I'll just put in the canonical. Oops, I'm not very good at these calligraphic C's. X there plus. Now the plus bit, let's go back to this piece here. So this is the flux transfer function. There's a dv by dp there and here. They both basically turn into the identity matrix. This one has to stay, of course, because I'm adding it, so it doesn't just disappear. So what I end up with is I. Those are the canonical transfer functions. The reason why we like to talk about the canonical transfer functions is because they have special properties, which we'll come to in another chapter. All right, but you can think of them as simply the transfer function that's been normalized by the strengths of the inputs. That's all basically they are. Okay. I think that's it for now. Of course, with this method, you can compute the frequency response. You get the same equations for the frequency response as we got before, except you swap, instead of S, you use J omega. Okay, and then everything is in the frequency response. So I don't think I want to say any more there. So I think that's it. If you have any queries, though, you can get in touch with me. I guess maybe just to mention for this pathway here, if you want to look at the frequency response for that pathway there with respect to the input x0, the Bode plots will look like, so this one will just go across and then dive down. That's the amplitude one, it's log frequency. And then the phase one, where we're in degrees, starts off at 0, then comes down and reaches either minus 90 degrees for x1 or minus 180 degrees for x2, right? So, and of course you will get different, you'll get a different amplitude Bode plot depending whether you have x1 or x2. They'll be slightly different. The gains will be different and the bandwidth will be slightly different, but the general pattern will be the same. Okay, I think that's it then. So that's it for chapter 18, and then next time we'll move on to chapter 19.